We're going to evaluate this indefinite integral as a power series, and then we're also going to find the radius of convergence. In order for us to do this problem, we have to review a couple of other topics. So some of the topics that I want you to review is the fact that the integral of 1 over a squared plus x squared dx is equal to tangent inverse of x over a times 1 over a plus your constant. Another concept that I want us to remember is that sigma, as n goes from 0 to infinity, of x to the nth power is equal to 1 over 1 minus x for x values that are less than 1 unit away from 0 or from the center. So let's begin with that integral, that first review concept. What I'm going to do is I'm going to let f of x be equal to tangent inverse of x. If we let f of x be equal to tangent inverse of x, then f prime of x is equal to 1 over x squared plus 1, or 1 plus x squared. And I want to tell you that this makes sense because if f prime of x is equal to 1 over 1 plus x squared, and if we take the integral with respect to x, with respect to x on both sides, then we can say that f of x is equal to the integral of 1 over 1 plus x squared dx. But what is f of x? Well, remember that f of x is equal to tangent inverse of x. So we can say that tangent inverse of x is equal to the integral of 1 over 1 plus x squared dx. And again, it makes sense because we've talked about it over here. The only difference is that in general we have a, and for our example, a is equal to 1. So we're going to start there. We are going to say that tangent inverse of x is equal to the integral of 1 over 1 plus x squared dx, which is equal to the integral of sigma, as n goes from 0 to infinity, of negative x squared to the nth power dx. We can expand this. We can expand this if we wanted to, and actually I'll show the work. If n is equal to 0, you have 1. If n is equal to 1, you have negative x squared. If n is equal to 2, you have a positive x to the 4th minus x to the 6th plus x to the 8th, and then the idea continues. So if we wanted to, we can substitute that in here. So we would have something along the lines of the integral of 1 minus x squared plus x to the 4th minus x to the 6th plus all the way towards infinity, and then we have dx. So when you integrate this, you have x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7, and then plus, and then we have your constant. This here becomes sigma. Let me write the constant first. We have the constant c plus sigma, as n goes from We can say 0 to infinity. And then we can say we have a -1. The first term is positive. And because the first term is positive, we can start it at n. And let me go back actually. X to the 2n plus 1 over 2n plus 1. Okay? And the reason why I need the 2n plus 1 is because we are looking at only odd powers. And then we are looking at the same numbers in your denominator. We can actually save all this work and do the following. So we have the integral of sigma as n goes from 0 to infinity, -1 to the n, x to the 2n dx. This is going to be equal to the sum as n goes from 0 to infinity of the integral of -1 to the nth power x to the 2n dx. But since we are integrating with respect to x, -1 to the nth power would be considered a constant, so we can move that right outside. And that is right outside of the integral. So this gives us sigma as n goes from 0 to infinity, -1 to the nth power. And then we have the integral of x to the 2n dx, which will be x to the 2n plus 1 over 2n plus 1 plus your constant. And again, I'm going to write that constant at the very beginning. So we can say c plus. So I want you to notice that when you expand it, it gave you the exact same answer as when you integrated the series here. Now, what is this last step here equal to? Well, that step is equal to tangent inverse of x. So let's say that tangent inverse of x is equal to some constant plus sigma as n goes from 0 to infinity, -1 to the n, and so forth. Well, what happens if we let x be equal to 0? If we let x be equal to 0, we have tangent inverse of 0 is equal to some constant plus sigma as n goes from 0 to infinity, -1 to the nth, 0 to the 2n plus 1 over 2n plus 1. Well, when you're adding 0 as n goes from 0 to infinity, that's just 0. Tangent inverse of 0 is 0. So you have 0 is equal to c plus 0, which means c is equal to 0. When we plug this value of c into that previous equation, we say that tangent inverse of x is equal to sigma as n goes from 0 to infinity, -1 to the n, x to the 2n plus 1 over 2n plus 1. So this here is a tangent inverse as a power series. Let me write that one more time. We have tangent inverse of x is equal to sigma as n goes from 0 to infinity, -1 to the n, x to the 2n plus 1 over 2n plus 1. Now, why are we doing this? Well, we're doing this because the original problem asked us to find the integral of tangent inverse of x over x dx. Let me bring this down here. So the problem that we started with was tangent inverse of x over x. Well, we have tangent inverse. Tangent inverse is that series. So if we multiply this tangent inverse times 1 over x, and again times 1 over x, then we can say tangent inverse of x over x is equal to sigma, as n goes from 0 to infinity, negative 1 to the nth power. Okay. Let's talk about this x over here. When you move it inside of your series, then you have x to the 2n, x to the 2n plus 1 over x. So that will give us an x to the 2n over 2n plus 1. Let me erase this here. Okay. So again, the idea is that you have x to the 2n plus 1 over x, and that's x to the 2n plus 1 minus 1, which gives you that x to the 2n. So what we want to do is we want to write tangent inverse of x over x as a power series, because remember, those were the instructions. So this is going to be equal to the integral of sigma, as n goes from 0 to infinity, negative 1 to the n, x to the 2n over 2n plus 1, and then dx. Okay, so one more time. We have sigma, we talked about why that is earlier, as n goes from 0 to infinity, and then we have the integral of negative 1 to the nth power, x to the 2n over 2n plus 1. Dx. Okay. So the integral of the sum is the sum of your integral. Or you can think about it as the integral of the terms. The integral of your series will be the series of the integral of each of your terms. Now, when you are integrating, when you are integrating with respect to x, then that negative 1 becomes a constant, so we can move that out here. And then the 2n, let me do this here. The 2n plus 1 in the denominator is also a constant because you're integrating with respect to x, right? So we can take that out. And then when you do this, let me clean this up a little bit more. We have sigma, as n goes from 0 to infinity, negative 1 to the nth over 2n plus 1. And then we have the integral of x to the 2n dx, which is what? We have sigma, as n goes from 0 to infinity, negative 1 to the nth over 2n plus 1. And now let's integrate. So this part here will give us x to the 2n plus 1 over 2n plus 1, and then remember, plus your constant. So I'm going to add that constant in the front. So we can say that this indefinite integral is equal to some constant plus sigma, as n goes from 0 to infinity, negative 1 to the nth, x to the 2n plus 1 over 2n plus 1 to the second power. There's a lot of concepts here. If you're not sure how we go from the integral of the sum to the sum of the integral, what you can do is you can integrate and then expand that series. So when you expand your series and then integrate, the next step will be to write the answers as a sum, as a power series. And when you write it as a power series, then this is what you should get. Let me erase this here. All right, I will stop right here. If you have any questions, let me know.